Hello everyone, this is Dr. Lennon, and this week we're going to be going over 3.4 and 4.1. So 3.4 is the product and quotient rule for derivatives. So basically the idea here is, although taking derivatives of sums and differences of functions behaves regularly, kind of as we would expect it to. So what I mean by that is, if you look at the derivative of some f of x plus g of x, the sum of two functions, and you take its derivative, that's just equal to the difference of each of the two summands added together. So f plus g of x, if you take its derivative, you get f prime of x plus g prime of x. But this is not the case for products and quotients. And we can see that with some basic polynomial examples. In fact, so let's look at an example to see why that's not going to work. So what I mean basically is, if you look at f prime of x times g prime of x and you try and take its derivative, it won't be f prime times g prime. So we want to show that with a counter example. So show f of x times g of x. If you take its derivative, it is not, in general, the same thing as f prime of x times g prime of x. So let's do that. So I'll give you the counter example that I'm going to use. So let's consider, by considering, we'll say f of x is just the linear function 3x plus 4, and g of x is the linear function 2x minus 5. Okay, so on the one hand, if we look at f of x times g of x, and we multiply those two together before taking any derivatives, this would be 3x plus 4 times the quantity 2x minus 5. And we can expand that by foiling, and we'll get 6x squared minus 7x minus 20. So again, your 3x times 2x gives 6x squared. Your outside is 3x times minus 5 minus 15x. Your inside is plus 8x, so negative 15 8x plus 8x is the minus 7x in the middle, and 4 times negative 5 is 20. So if we try and take the derivative of this thing that we've expanded, f of x times g of x, and we take its derivative, we can just look at the expanded polynomial, and we would get 12x minus 7, and that is our derivative. But what if we tried to do it the other way? What if we tried to take the derivative of each of the parts first? So if we did that, f prime of x would be the derivative of 3x minus 4 is just 3, and the derivative of 2x minus 5 is just 2. So if you tried to multiply those derivatives when taking them first, so if we look at f prime of x times g prime of x, that's just equal to 6, 3 times 2. So basically, we can see that this thing and this thing, these are not equal. So that showed that in general, this method is not going to work for finding the derivative. So let's note that. We see that in general, the derivative of a product of functions is not the product of their derivatives. So that begs the question, well, hopefully there's a way to do this, and we're not going to go through the proof of that method. I'm just going to tell you the formula, and then we're going to apply it to the classes of functions that we're studying in this class. So here is the product rule for derivatives. So what does it say? So we'll say let u equal u of x and v equals v of x be differentiable functions of x. So then usually what we do, so we don't kind of crowd up the sheet with these formulas, is rather than writing u of x and v of x, we're just going to write u and v and understand that those are both functions. So then what does the product rule say? It says, well, if you're trying to take the derivative of the functions u multiplied with v, what that is u prime v plus uv prime. So let's confirm that this would work in the previous example. So in the previous example, what did we have? Well, let's call f of x u. So u would have been 3x plus 4, and v would have been 2x minus 5. So u prime is 3, and v prime is 2. So then what the product rule says is essentially what we want to do is kind of multiply diagonally and then add to get our derivative function. And anytime we have more than one term, we want to be sure to put that in parentheses. So in this case, our derivative function uv prime is going to be 3 times the quantity 2x minus 5 plus 2 times the quantity 3x plus 4, and then we can just expand and simplify. So we end up with 6x minus 15 plus 6x plus 8, and this simplifies to 12x minus 7. And if you check above, that's exactly what we got using the correct way of multiplying it out. So 12x minus 7. So we get the same answer. That was the correct way. So basically, to find the derivative, 12x minus 7 was correct in the previous example, and 6 was the incorrect answer. So this way will give you the correct method. We also have the quotient rule for a quotient of functions, which is a little bit different. So if you're dividing them and you don't want to try and rewrite it as a product, the quotient rule, again, we have two differentiable functions of x, u and v, and what it says basically is if you have the quotient u over v and you want to take its derivative, this is u prime v minus uv prime divided by v squared. Okay, so again, really what we want to do is just be sure that we're getting the setup correctly here and plugging things in. So we'll see how to do that. Notice there is a minus, so you don't have the symmetry in top that you do in the product rule. Since the product rule is a plus, you can kind of change the order around and it won't matter. So let's look at an example here where we just want to differentiate, find the derivative of each function. So let's suppose we have f of x equals x squared times e to the 3x minus 1, so only that 3x is in the exponent. Again, with these product and quotient rules, the derivatives might not be nicer. They may just get messier and messier, kind of like we saw with the chain rule. So usually I won't require too much simplification here. So for this one, we want to let u be the first factor, x squared, and v be the second factor, e to the 3x minus 1. So u prime, we're just using the power rule, 2x. V prime, the derivative of 1 is, the minus 1 is just going to go away. And then remember the derivative of a continuous exponential function, we just bring the constant down. And it remains e to the 3x, so 3e to the 3x. So our derivative here, f prime of x, is going to be 2x times e to the 3x minus 1 plus, so again we're multiplying like this one and this diagonal. So x squared times 3e to the 3x. Normally what I do is I write the constant in front, so I would write this 3x squared e to the 3x, and I would just leave it alone like that. No reason to try to perform any simplification there. All right, let's look at another example where we do the quotient rule here. So, let's say our function is g of x equals e to the x divided by x cubed minus 5x. So here what we want to do is, again, we're still going to set up u, v, u prime, and v prime, but we have to use that different quotient rule formula. So here u is e to the x, v is x cubed minus 5x. So u prime is e to the x, and v prime is 3x squared minus 5. So according to the quotient rule, how does this go? Well, again, the order matters on top because there's a subtraction, which is not going to be commutative. So we need first u prime times v, so that's my x cubed minus 5x times my e to the x, which is u, and then I need to subtract v prime times u, so that's 3x squared minus 5 times e to the x, and then I'm dividing everybody by v squared. So v was x cubed minus 5x, so I'm going to do x cubed minus 5x, and then I'm going to square the whole thing. And I would just stop there. You know, there may be some things that you could combine. It actually doesn't look like it if you expand them, so I would just leave it alone as is. So let's go ahead and look at some more examples. Again, with these, it's just kind of practice makes perfect. So let's look at a couple more. So let's say we have C, we have f of x equals the square root of x times e to the 2x. Again, it may be helpful for you to so we're going to write u, and rather than write the square root of x, let's just write this as x to the 1/2 power. Remember, the square root as an exponent is just 1/2. So this is x to the 1/2. V is going to be e to the 2x. So we apply the power rule to find u prime. So that's going to be 1/2 x to the minus 1/2 because it's just a power function. And then v prime, we have a continuous exponential function. So we write this as 2e to the 2x. So again, remember there's two different rules between finding u prime and v prime there. So then, again, f prime of x this is the product rule, so we just multiply diagonally and add. So we have 1/2 x to the minus 1/2 e to the 2x multiplying by v plus, now I want to multiply 2x to the 1/2 e to the 2x, that's multiplying u by v prime. And if I want to be extra nice, I can write this using the square roots that they started with. So e to the 2x would remain on top in the first term. 2's in the denominator, so it stays there. And then x to the negative 1/2 is just a square root of x in the bottom. And in the second term, the x to the 1/2 will just turn back into the square root of x. And we could write our final answer like that. Okay, let's look at D. So let's look at a quotient again. So let's say we have g of x equals x cubed minus x squared divided by the natural log of x. So we're using the quotient rule here. U is going to be the numerator, x cubed minus x squared. V is the denominator, the natural log of x. U prime is 3x squared minus 2x. V prime is 1 over x. So the quotient rule, again, remember that says we need to do u prime v minus uv prime divided by v squared. So u and u prime are both going to need parentheses when you write them down because they have multiple terms. So we have 3x squared minus 2x times the natural log of x minus x cubed minus x squared times 1 over x. And then everybody is being divided by the natural log of x quantity squared. So I would maybe do one simplification. So in the top, 1 over x can cancel with x cubed and x squared if you distribute it. And you can also distribute the negative. So I'd leave the first part alone, 3x squared minus 2x, natural log of x. And then I would end up with a minus x squared and a plus x, distributing both the 1 over x and the negative sign to eliminate the parentheses. And then I have natural log of x quantity squared in the bottom. So that would be the quotient rule for part D there. Okay, so let's go ahead and continue with just a couple of more. Let's do 2 more practice examples, and then we'll look at a way where we can use both the product and the quotient rule to find a derivative to kind of see the similarities and differences between the techniques. Okay, so that was E, so part D, so now we're on E. So E, let's say we want to take the derivative of, this time we have f of x is x cubed plus 1 times e to the minus x. Sorry, I'm left-handed, so I keep hitting this button accidentally on my tablet. So u is going to be x cubed plus 1, and v is e to the minus x. So u prime is just 3x squared, and v prime, remember we're going to treat that negative like a constant when we're using this exponential rule, so we get minus e to the minus x. So f prime of x, again, we just do u prime v minus plus uv prime. Excuse me. But in this case, there's a negative from the negative e to the negative x and v prime, so we can think of that as just being subtraction. Anyhow, we get 3x squared, e to the minus x, and then I'm going to get minus from the v prime, and then in parentheses, x cubed plus 1, e to the minus x. And that would be our derivative. So pretty straightforward. Again, if you have e to the minus x, you still have to treat that negative as if it's a constant. Okay, so last practice example from this example set. Let's look at g of x equals 5 raised to the x power divided by 8x squared minus 3x. So my u is 5 to the x, and my v is 8x squared minus 3x. So one thing to remember here, my standard exponential function, the way you take its derivative is the derivative of b to the x would be the natural log of your base times that base to the x. So here the base is 5, so my u prime should be the natural log of 5 times 5 to the x, and v prime here is going to be 16x minus 3. So we apply the quotient rule and we get g prime of x is, let's say, 8x squared minus 3x times the natural log of 5 times 5 to the x. That's multiplying u prime by v. Now we need to subtract. Again, put v prime in parentheses, 16x minus 3 times 5 to the x. And everybody is being divided by v squared. So 8x squared minus 3x quantity squared, and that is that. Okay, so again, these formulas are kind of all about the setup, remembering your basic formulas, and then just kind of plug and chug with the formulas. So let's look at one last example. So let me start this on a new page because I want to do it in 2 ways to show that sometimes you can use algebra to rewrite something and use the product rule rather than the quotient rule. So let's look at this example. So what we want to do here is let's differentiate using both the product and the quotient rule. So what is our function? Our function here is f of x equals the natural log of x divided by x squared. So again, let's do method 1. The straightforward way is to apply the quotient rule. Because it is already a quotient of functions. So doing that, we would have u is the natural log of x, v is x squared, so u prime should be 1 over x, and v prime would be 2x. So then over here I can write my f prime of x as u prime v, so 1 over x times x squared minus uv prime, so that's 2x natural log of x, with everybody being divided by v squared, so x squared quantity squared. So the top 1 over x times x squared is just x, so we get x minus 2x natural log of x over x to the 4th. And you might see you could even perform some simplification here. A lot of times there might be some simplification you could perform just because the quotient rule is kind of set up in a way so that your entire thing is set up as one fraction over a common denominator. So what is the simplification? Well, I could actually factor out an x on top and get 1 minus 2 natural log of x over x to the 4th. And normally I would not perform this simplification just due to the fact that it's fine the way it is, but I'm just doing it here because I want you to show that typically the product rule is going to give it in a slightly different form. So basically this x will cancel with this power and it will become a 3. So we can write this as 1 minus 2 natural log of x over x cubed, and that would be the derivative from the quotient rule. So the second method is using the product rule. So as is, we cannot apply the product rule to the function as it's written, but we can use some algebra to rewrite it, and in doing so, we can make the product rule available to us. So how do we do that? Well, f of x was originally what? It was natural log of x over x squared. So we can rewrite f of x as, so it was natural log of x over x squared. Well, that looks like a quotient, but it looks like a product if we write it as the natural log of x times x to the negative 2nd power. And then when it's written as a product, we can apply the product rule. So here u would be natural log of x, v would be x to the negative 2nd, u prime would be, again, 1 over x, and v prime would be minus 2x to the minus 3. So then our product would look like, using the product rule, 1 over x times x to the negative 2nd plus my negative 2x to the negative 3rd natural log of x. And this would come out as 1 over x cubed minus 2 natural log of x over x cubed. And we see that now both of those fractions have the same denominator of x cubed, so we can just put the numerators together as one fraction. 1 minus 2 natural log of x over x cubed, and we see we get the same exact result when we apply the product rule as when we apply the quotient rule. We just had to use some algebra to clean it up so it was in a form fit to apply the product rule. Okay, so that's it for the product and quotient rule. Again, these take a lot of practice. The next homework is available online, so please reach out to me if you have any problems there, and I'll be sure to answer questions in the next video. So this is Dr. Lennon signing off.